Okay, so I'm going to be talking about chance-constrained routing in mobile networks. And this is a joint work with Matteo Cacciola, Frangioni and Giovanni Stea from the University of Pisa. So, a little bit of context. We're talking about mobile cellular networks, which today play a very important role in emerging IoT applications. And the characteristics of these applications is that basically they need to route messages in a local area, which is not too wide. And but we have constraints about timeliness and reliability. And by reliability, I mean probability of reception of these messages. And usually the target area is defined by the application itself. So traditional LTE tools can indeed support these services, but they are rather unsuitable because they require too much energy. So recently a new communication framework has been proposed, which you can see in the picture. So basically we have the antenna and the user equipments, which are represented here in the figure. Now what happens is that the antenna sends the message to the users, and then the users communicate by themselves by broadcast. So basically we have two different types of transmissions, two different types of communication channels in this new framework. The vertical transmissions or downlink communication channel in red, this arrow, which goes from the antenna to the user, and the green ones, which are called horizontal broadcast or device-to-device communication channels, which happen between the user equipments. Okay, so two different types of communications: downlink from the antenna to the users, and device-to-device from one user to another user. Of course, this could be this arrow could be reversed, so every user can communicate to any other user. Now, these two types of transmissions, apart from being different because they involve different types of elements in our framework, in our system, also have different characteristics in terms of reliability and cost. When I say cost, I mean energy. So vertical links are reliable but costly, horizontal links are free but not reliable. And the other important feature that user equipments, which communicate via horizontal device-to-device broadcast, can act as multi-hop relays. So horizontal transmission are shadowed by the antenna, which issues grants to the users that may transmit. So basically what happens is the antenna at every different stage tells the users if they can communicate or not. And if they're allowed to communicate, then they can transmit to the other users via broadcast. So from a technical point of view, if we're given the position of the user equipment, transmission power, modulation, coding scheme, we can then model the probability that a certain horizontal transmission is successful. And so we can define the chance-constrained unicast multicast routing problem, which is the problem of selecting vertical and horizontal multi-hop transmissions, the red and green arrow, to guarantee that all the users receive the information with a certain level of reliability and within a given time limit with minimum energy cost. So this will be our objective function, and these will be our constraints. So we can model the system as a graph, dialectic graph, where n is the set of vertices and a is the set of arcs. Basically, n consists of node 0, which is the antenna, and the rest of the node n and prime, which represents the user equipment. And the arcs are partitioned into two different types of arcs, the red one and the green one, which of course match the different types of communication channels that I just mentioned. So vertical arcs A first correspond to downlink transmissions from node 0, the antenna, to any user equipment I in N first. So these transmissions have probability 1 of being decoded successfully, fully reliable, but are very costly. And then arcs A in A second, the green ones, horizontal transmission broadcast, IJ, where these are user equipments, of course all different from J, and these are device-to-device transmissions, which are not fully reliable, so they have probability less than 1 to be decoded successfully, but they are rather cheap, so low energy cost. And our problem is to transmit from the antenna to the entire flow plan. So this is our goal. All the user equipment must receive the message at the end of the process. The process takes place in stages. So we have the initial stage, which is a special stage because in this stage the antenna transmits via vertical, via downlink. Transmits the message to a subset of users, not all the users, because otherwise the problem would be trivial. Of course, all the users will get the message, but probability 1 of them will be very expensive. So we want to minimize the number of vertical transmissions because they're very costly. But anyway, we need some of them. So some of the users will receive the message via downlinks with probability 1. In the first stage, and then in the following stages, only horizontal transmissions are allowed. This is why we call the multi-hop, multi-stage process. A node I in N first, which corresponds to user equipment, can issue an horizontal transmission at a given stage only if granted permission from the antenna. So remember that the antenna controls the horizontal transmissions. And at most m grams can be assigned in each stage, and we have at most k stages because we don't want the process to take too long because we have time restrictions. And at the end, each user equipment must receive the message with probability at least alpha. So this is our quality of service requirement. And the objective is to minimize the number of vertical transmissions as well as the number of grants. So now we come to the mixed integer nonlinear programming model. We have 3 different types of variables. X variables that are binary correspond to the first stage variables. So these are variables which select the user equipments that receive the message with probability 1 at the very first stage. Then for the following stages, we have 2 different types of variables: probability variables, which are continuous and 0, 1, and grens variables, G variables, which for every node basically map if that node is granted transmission in a particular stage. So we have 2 indices, node I and stage H. So this is the probability of receiving the message at stage H for node I, and this is 1 if node I is granted transmission at stage H, 0 otherwise. So this is the model, which is a mixed integer nonlinear model. Of course, we have continuous and binary variables at the same time. We have the objective function, which minimizes the number of vertical transmissions at first stage and the cost of grants in the subsequent stages. Okay, so number of vertical transmissions and number of grants, weight, some proper weight, which is a coefficient that we decide. Constraints 3 impose that each user equipment node I in N first is ultimately stage K is reached with probability at least alpha. So this is the chance constraints that we have. So we want constraint 3 says that every user equipment must have probability PIK, which is the probability of receiving the message, stage K, which is the last stage, least alpha, and this is connected with constraint 4, which is the chance constraint of our problem, which is the nonlinear constraint, which basically models how the probability propagates from the antenna to the rest of the floor plan, depending on the probability of reception and the grants. So constraints 4, the red ones, are the difficult constraints, chance constraints. And finally, constraints 5 bound the total number of grants available, which is what we mentioned before. So the number of grants at every stage is limited. So without the chance constraints 4, the problem would be, without these 4, it would be almost trivial. But these constraints 4 make the problem very, very difficult. The first observation is that we can take the log and transform these constraints 4. Now there's a little trick that we need, because it is ill-defined with probability. When probability is equal to 1, but of course we can take a constant slightly less than 1, arbitrarily close to 1, and we can get around this problem. So we rewrite constraints 4, chance constraints 4, with the log, and this is what we get, which is something which is still nonlinear, but it's linear with respect to variables g. Okay, and we have no continuous variables on the right-hand side. And at this point, what we do is a Lagrangian relaxation of the chance constraints once we have applied the log. So the chance constraints, after applied the log, are moved into the geographic function with these Lagrangian multipliers. And it turns out that this problem decomposes into k subproblems. So basically one problem for every stage. Now the subproblems are different depending on which stage we look at. In particular, we have 3 different types of subproblems. The first subproblems, which corresponds to stage 1 and contains variables xi and gi2, which are the grants variables for stage 2, with I in n-pairs, so user equipment. If we collect like terms, and so there is no point in setting g to 1 if xi is 0, then we can rewrite a problem in this way, which is where the nonlinear operations basically are applied only to constants. So this is 0, 1, and p. But this is an easy problem that can be solved in O n log n, basically by sorting. So this is the complexity of sorting. So subproblem 1 is easy, O n log n, order of n log n. Then we have a second type of subproblem, which applies for the second subproblem for the second stage out to the second to last stage, k minus 1. And these subproblems contain variables GIH plus 1, so stage h plus 1, and PIH. So we have grant variables and probability variables with respect to stage h plus 1 and h for all the nodes. This is the problem. And in this problem, each variable PIH interacts with a variable GIH plus 1. And of course, the term is highly nonlinear. Now, the point is that G is binary. So if we distinguish the two, we consider the two cases 0 and 1, compute these two constants for G equal to 0 and G equal to 1. So if we have these constants, then the subproblem H for H equal to 2 up to k minus 1 can be rewritten in this form, which can be easily solved in, again, O n log n, just sorting. The problem is how we compute these constants, PIH0 and PIH1, the constants corresponding to G equals 0 and G equal to 1. Now, for G equals 0, the problem is trivial because we minimize this monotone function and this interval, and the optimum is one of the two extremes. But computing PIH1 is a bit more complex. It is still a one-dimension minimization problem in this form, but it requires a little bit of work. Basically, we use the simple globalization of Newton's method. And finally, for subproblem K, the last subproblem, which is the subproblem corresponding to the last stage, we have variables p, I, k for all the i's is separable over I. The objective function is convex because the lambda are greater than or equal to 0, so the optimum is the left point. So p, I, k equals of. Now, to solve the Lagrangian dual problem, we use the bundle method, and basically from an algorithmic point of view, we use Lagrangian heuristics and Lagrangian-based branching bound. I won't get into the details of these because it would take too long, but basically the heuristic is sort of greedy based on the scores that come from the solution of the Lagrangian problem. And the Lagrangian-based branching bound is just a very straightforward branching. It's based on a straightforward branching rule, do one fixing of the binary variables. So we get to the experiments now. We used realistic scenarios which our colleagues from the engineering department produced using a simulator. Instances are distinguished by the number of user equipments, the radius of this local area in meters, and the coverage probability, which is the quality of service requirement. We compared with Barron and a Taylor heuristic that was implemented by engineers. And we conducted 2 different types of experiments with 2 different time limits, 5 minutes and 50 minutes. So for 5 minutes, the columns corresponds to, this group of columns corresponds to the description of the instance, number of user equipments, radius in meters, and probability level. These are the results for Barron, these are the results of the branch bound, and this is the results for the combinatorial heuristics designed by the engineers. Basically, only the 10 user equipments could all be solved to optimality within 5 minutes. Our method is generally more efficient than Barron, which pays to solve 2, except for larger radius, where Barron closes at the root node for some reasons, but and the combinatorial heuristic is generally extremely fast, but is pretty far away from the optimum. So we have both the inherent gap and the primal gap and dual gap to distinguish whether we want to measure the quality of the upper bound, lower bound, and just the inherent gap of the algorithm that we consider. For larger instances, so number of user equipment equal to 25, we can solve half of them with our method. But for n equal to 50, then basically there is no hope to solve them, even with a larger time limit of 3,000 seconds, so 50 minutes. Now, if we compare our branch-bound method with Barron, we can see that for larger instances, the lower bound and the upper bound, especially the upper bounds of Barron, are quite useless, whereas upper bounds are still kind of in a useful range, even though the gap can be pretty large. So we cannot say that we can solve these instances. We're still pretty far away from solving them. But if we compare the performance of our algorithm from that of Barron and the combinatorial heuristic, then our gaps are fairly small. So what we can say at the moment is that if we compare with Barron and the combinatorial heuristic, the branching bound that we designed and we implemented performs better, but there is still a lot of work. until we are able to solve these instances.